Containerization technology encapsulates applications into portable units, allowing for consistent deployment across varying environments. Containers package an application and its dependencies, ensuring compatibility and minimizing inconsistencies when deploying to different infrastructures, including cloud, local, or edge devices. Tools like Docker enable developers to build, share, and run containers quickly and efficiently. Utilizing containerization aligns well with generative AI solutions, enhancing portability and scalability, especially in distributed or resource-constrained edge computing scenarios where device specificity might vary greatly. Edge computing refers to processing data at or near the source of data generation, significantly reducing latency and bandwidth use. Edge devices range widely, including IoT sensors, local gateways, smartphones, and dedicated hardware platforms, e.g., NVIDIA Jetson, Raspberry Pi. Deploying generative AI solutions to edge devices addresses the challenges of latency-critical AI tasks by bringing computation closer to the data source. It also addresses connectivity issues and data handling constraints in decentralized environments, ensuring real-time interaction and increased security through reduced data transit. Reduced latency. Performing AI inference locally on edge devices ensures immediate response and smoother user interactions. Bandwidth optimization. Processing data locally reduces the volume of data transmitted, conserving bandwidth and reducing network costs. Enhanced security. Fewer data transmissions minimize security risks, adhering to data privacy regulations. Portability and scalability. Containerized AI models simplify application updates and scaling, allowing effortless deployment across diverse devices and environments. Offline operation enables AI applications to function independently from cloud services, ensuring operational continuity during connectivity disruptions. Choosing the optimal container technology impacts your solution performance significantly. Popular container technologies include Docker, most frequently utilized for building and deploying containerized applications, providing mature tooling and wide adoption. Kubernetes manages containerized workloads, ensuring orchestration, scalability, and high availability. Azure Container Instances, ACI, offers simple serverless deployment for containers in Azure. Azure IoT Edge, specifically tailored for edge device deployments, integrating seamlessly with Azure ecosystems to manage complex AI workloads. Consider the technology stack, scalability requirements, integration complexity, hardware capability, and performance criteria to determine the most suitable container solution. Docker simplifies application deployment through lightweight, isolated, portable containers. With Docker, generative AI models and their requisite runtime environments can be packaged efficiently, creating consistent deployments. Edge devices benefit from Docker through efficient resource utilization and ease of version control. Docker's layered architecture significantly reduces update overhead, facilitating rapid iteration. Example Dockerfile snippet. Dockerfile from Python 3.9 slim copy. /app workdir /app run pip install are requirements that txt-cmd python run _ai inference.py. Azure IoT Edge extends cloud computing capabilities to edge devices seamlessly. It is designed specifically for Azure services integration, particularly advantageous for AI and machine learning workloads. IoT Edge comprises runtime modules, tools to manage containerized workloads, and communication security between devices and Azure services. Key capabilities: simplified deployment and management of containers, scalability solutions for edge AI, secure credential management, integration and orchestration with Azure Cloud Services, offline capabilities, and local-centric computation. These features enable effective AI model deployment directly to edge, ideal for sophisticated generative AI use cases. When designing deployments, key considerations include hardware compatibility and resource constraints of edge devices, network availability and reliability, model size and computational complexity, security and compliance requisites. Maintenance and update strategies clearly define deployment patterns. Single container deployments for simpler applications. Multi-container orchestrations for complex solutions like integrated generative AI and data aggregation plan deployment. And contingency strategies, ensuring that edge devices adequately handle containerized workloads seamlessly under various operating conditions. To deploy generative AI models effectively, it is essential to select and optimize models appropriate for edge hardware capabilities, containerize applications, ensuring minimal runtime and dependence, overhead validate container performance locally before distributing use-based images optimized specifically for AI scenarios, lighter runtime environments like Alpine Linux, and tools like Docker multi-stage builds to further minimize container size and enhance performance. Leverage container registries, e.g., Azure Container Registry, to securely store, version, and manage container images, simplifying operational lifecycle management. Azure IoT Edge implementation steps. Create AI container. Package and push a container to a container registry, like Azure Container Registry. Define deployment manifest. Specify configurations within a deployment manifest file, defining module identity, versioning, and routes for inter-module communication. Device configuration. Register edge devices within Azure IoT Hub for centralized tracking and management. Deployment itself. Distribute deployment manifests through IoT Hub to edge devices for remote automated application updates. Monitoring and updating. Continuously monitor health, performance, and manage updates through integrated IoT solutions provided by Azure. Deployment manifest specifies settings and modules present on Azure IoT Edge. They follow JSON schema, identifying module configurations, routes for message passing, and module-specific configurations, such as environment variables. Essential properties in manifests. Modules content. Defines module container details. Routes. Dictates inter-module and cloud edge communication pathways. Manifest example. Simplified JSON modules content. $agent. AI inference. Settings. Image. My registry. Azure Circ.io/AI-container:v1. Routes. AI output. From/messages/modules/AI inference/outputs/* into $upstream. Monitoring ensures optimal performance, reliability, and security of generative AI containers. Azure IoT Hub Insights centralizes performance and reliability data collection, enabling efficient health monitoring of deployed containers. Container logs and metrics. Azure Monitor and Log Analytics gather detail-rich data for advanced diagnostics and debugging. Resource monitoring tracks CPU, memory, and networking resource use, facilitating performance optimization and resource planning. Alerts and notifications. Immediate alerts highlight potential issues for prompt action, maintaining operational continuity and mitigating service disruptions. Deploying AI containers may introduce challenges such as resource constraints, edge hardware scaling, or performance limits. Connectivity issues. Intermittent connections influencing cloud synchronization. Deployment failures due to manifest mismatches, container misconfigurations, or network security. Troubleshooting guidance. Regularly examine logs from edge devices and modules. Utilize IoT Edge runtime CLI tools for direct, local diagnostics. Validate container integrities and replicate local testing to uncover practical discrepancies. Maintain updated documentation and contingency processes for fluid troubleshooting approaches.